Okay. Hi, everyone. First of all, thanks so much to the organizers for putting this together and inviting me to talk to you today. I got a lot of warning emails that the background of people is really diverse, so we should keep it simple. And I also will have a pleasure to talk about more like technical stuff at the conference next week. So I thought I'm gonna prepare just a very like simple illustrative examples of how we are dealing in a contents matter with discovering new physics and learning phases of matter. And then I will finish by posing you some questions. And hopefully we can talk to each other and get inspired with what you guys are doing in the other fields. Before I start, just hands up, who is condensed matter? Who is high energy? Ooh, Astro and Cosmo. Okay, I see. So we have a mainly high energy physicist, but I know that you guys are mostly already big experts on machine learning, so that's great. Yeah, so just a quick slide about my background. I am from Delft University of Technology in Netherlands, and we are basically working on the overlap of like these three fields. I am super interested in combining the sort of techniques that have developed independently in one and applying them to the other, and that's sort of how this AI angle also appeared for me in my research. So before I get more to the concrete examples, I just want to give like a super quick overview about what are we doing in quantum physics more broadly with machine learning. So the first thing is discovering new physics from data. This is very high level what I'm gonna talk to you today. Basically, in like a condensed matter and quantum information, we solve the problems by experimentalists maybe measure something interesting, or maybe they don't even measure anything, but we just write some complicated Hamiltonian and then we try to solve it. And then we solve it, and eventually we discover something interesting. And now this sort of data-driven approach is very antithetical to that. And now we are at this interesting stage that we have a lot of methods that we can apply to raw measured data from the experiments and see if we find something interesting. So this is sort of the angle I'm gonna go into today. But just to mention few other things, just to spike your interest, then come talk to me after if that sounds fun to you. There is a lot of interesting stuff going on in automated control of quantum devices. That's another a large interest of mine. Basically, if you want to build the quantum computers with many qubits, the control, like the amount of control parameters does not scale well, to put it mildly. So there is a lot of opportunity for using, basically machine learning algorithms to implement this complex data that we are measuring and decide the next steps in the experiments. Then there is this sort of thing that I guess happens across physics, that you are using generative models to design new quantum experiments or design new quantum material in condensed matter, stuff like that. This other thing I'm going to touch on a little bit later, and that's efficiently approximate quantum states. So I'm gonna give you a whole slide on this because this is a motivation why quantum physics poses some interesting challenges for machine learning, but you may already know that the central objects we are studying, quantum wave functions, they do not scale great with a system size. Anyone wants to tell us how does number of degrees of freedom in a quantum wave function scales with a system size? Yeah, exactly, perfect, exponentially. So if you have a system of 50 qubits, you need 2 to the 50 variables. So there is a lot of variational efforts going into approximating these things. And related to that, you want to develop approximative numerical techniques to benchmark and simulate quantum computers. And also related to that, maybe discover and optimize quantum algorithm. One of the organizers here, Florian Marquardt, is an expert on that. I'm not sure if he was at some point giving a lecture about this topic. But okay, back to the subject matter here. So my talk was called Learning Phases of Matter. So first I'm gonna quickly motivate why we care in physics about phases of matter. And then I am gonna give a quick walkthrough on how we approach discovery of phases of matter with machine learning. And then I am gonna mention some of this aforementioned open questions. So in condensed matter physics, phases of matter are actually super, super important because all the cool things that we are using, for example, in quantum technologies, like a superconductivity and all this like complicated phases that we spend a lot of time studying, like quantum magnetism, or maybe you heard about Bose-Einstein condensate, they all come as a new phases of matter when you describe some complicated quantum system and you try to understand what's the behavior of that system. So when we say, yeah, in condensed matter or in quantum physics phases of matter, it spends a huge amount of what we are studying because that's really the main thing we care about. It's not just water turning into ice. It's like superfluid turning into a weirdly paired phase and stuff like that. And as I was saying before, before this sort of more data-driven methods trickled down to condensed matter, which in our context was back like 2016, 2017. I know that you guys in you guys in high energy have been at it much longer than us, but the sort of traditional approach was exactly like, I am gonna sit for a long time, write some model that we call Hamiltonian. Then I am gonna think much harder, either develop an analytical or numerical technique to solve it. And then I am gonna study the properties of the wave functions that I get and hopefully discover some of the new physics. Of course, this approach has obvious limits, right? Because if I don't have a great idea, for example, in the case of the superfluidity, you need to feel inspired and be like, let me try to write down what would happen if the whole system would sit down into the perfectly coherent quantum ground state. If you don't know this, it's tricky to like solve everything. So that's why there was a lot of interest into this kind of research. And then really the really like a figure of merit here is that we are just gonna measure a lot of experimental, maybe projective data or correlators or expectation values, or we are going to simulate those things. Then we are going to unleash some data-driven algorithm on this data and hopefully discover something from that. So I just I know you guys are mainly already experts, but I will just give super quick walkthrough on this wave function and how this like big amount of data comes about in quantum physics, just so we are like 1000% on the same page. So as I was saying, we are using these wave functions, which are just like a complex vectors to describe different quantum states. And then this exponential scaling is really this, that for 2 spins, I need vector of the size 4. For 10 spins, I need a size 1000, and for 100, it's 10 to the 30, right? And the reason this happens is this everyone always says this, right? The main difference between quantum and classical is that the qubit can be anything between 0 and 1. That has nothing to do where the speed up in quantum computing comes from, but it has something to do where the complexity of these quantum states comes from. Because if I would then have these two states that either you are on an upper ladder or a lower ladder, classically I'm only up or down. So if I have n of them, I just need n numbers to describe the whole thing. But if I have these systems that both can be anything, then I need one number for 0, 0, 1, 4, 1, 1, 1, 4, 1, 2, 1, 0, 1, 4, 0, 1. Then imagine if I write this for 3 qubits, I'm gonna get 8 and so on. So because I sort of, now I can have all the combinations of everything, then every single of these coefficients matters. And this is really the key underlying thing why quantum computers have such a powerful like complexity, and why we cannot simulate them classically, because after 20 qubits I ran out of the memory in my computer. And this is also the core reason that I cannot just be, let me write this Hamiltonian for a quantum magnetism for 1000 spin, diagonalize it and celebrate, right? Because I just physically cannot solve it exactly, right? And then there is this other angle, that these wave functions I just described, they are some complex vectors. And if you think about how you would measure complex vector, you quickly realize that that's a tricky thing, right? You can measure like real things. You can project in some configurational basis. You can measure expectation value. You can have some sensing device next to it and measure current through it. But inevitably what happens is that you are, every time you measure your wave function, you project on something, and that something has much less information than your original Hamiltonian. So that's also another thing, that even if I'm studying a single wave function, I need to sample from it super much to be able to calculate expectation values, correlators, the kind of quantities we care about. So yeah, so this is just to say that like we are not accumulating big data in a like a LHC sense kind of big data, but we are still accumulating them, because even like if I am simulating system of 10 spins that have some complicated interaction with each other, I need to accumulate tens of thousands of measurements to have enough data to effectively characterize the properties of my systems, exactly because of this exponential scaling that I just explained you, because the wave functions, they contain so much volume of information. And now we are living in an awesome time, because no matter what your fields, probably you heard about different big companies publishing. Now we have 50 qubits, now we have 100 qubits, now we can do this and that. We are far from all of this practical advantage that people are hunting for, but people are easily building in the academic and industry labs nowadays systems with hundreds of quantum particles, where we are exactly in this regime that I cannot simulate it, but I would really love to learn something from what I measure or verify that it works, stuff like that. Okay, so I prepared here like a tree branch of different methods that we are looking at. I think you are probably familiar with most of them, but I'm sort of gonna walk through how we are using them in the settings of doing measurements on the wave function and trying to learn something from them. I'm not gonna cover everything. I'm just gonna pick like a simplest path through this tree, and then we can have a discussions afterwards about different things that they cover. So the first things first, again, I feel like it took us longer than in other fields of physics to realize it. You don't need a deep neural network to do most things, right? Clustering methods are very powerful. So I'm just gonna show simple examples of some linear, nonlinear clustering techniques. Then we can move to neural networks and show the first sort of pilot examples of a neural networks in condensed matter physics, which was supervised learning. And then I'm gonna show two methods that are unsupervised and, let's say, more practically tiered towards the discovery, and that's learning by confusion and using predictive models. And then we can discuss some open questions, and I think these open questions may be probably similar across different disciplines. There are things that we can easily simulate and then we can easily predict, but then there are specific things that are hard to simulate and then also hard to predict. So the boundary where the knowledge is kind of well-defined by what we already know, then there is an interpretability, and then there is a path towards actually discovering new physics from the data, not just confirming where the phase transition lies that we know from some Russian paper from 80 years ago. Okay, so let's start with the clustering. For statistical and condensed matter physicists, our sort of toy model example that we learn, and I guess everyone was a physics student at some point, so I think you probably saw an Icing model on 2D lattice. Hands up. Who? Super, everyone. Yeah, so I also set up some code for the stuff that I'm gonna talk about. So if you wanna go to eliskagreplova.com/GGI, you can look at the notebooks, but it's not necessary to follow the lecture today. But yeah, okay. So the Icing model is on a 2D lattice, is specified by this Hamiltonian that gives you energy minus J if the spins are like this, and energy plus J if the spins are like this. So this is better for your lowering the energy of your system. If you start adding temperature into this system, Boltzmann distribution tells you the probability of a specific configuration at the given temperature. But effectively, what it physically does, the temperature adding, is the difference between this and this becomes smaller to the degree that eventually you will have a phase transition. But okay, now everyone is already familiar, but just a quick quiz. Which of these has then the lowest energy? Sorry? C? Are we sure? A. It's A, because you want to minimize the number of those, right? So, and actually in C, in A, you have left. Yeah, and okay, and then you start adding the temperature, and the difference stops mattering, and then at some point there is some phase transition, and the system, instead of aligning everything, it just sits randomly. And so this is the phase transition you studied in school. I don't even remember the calculation anymore. It was like 2 pages of this Onsager solution. And then you calculate, and you get this critical temperature. And you also understand that the magnetization is an order parameter in your system. So then the question is the following. Let's say that I forgot everything from my second year statistical physics, but I know how to do a Monte Carlo algorithm to sample all of these configurations. Can I, without knowledge of the Hamiltonian, without knowledge of the parameter, just look at the configurations and understand where this phase transition is? And so the answer is going to be yes. You can actually use just like the simplest linear clustering techniques, which is called principal component analysis. Again, give me hands up who knows. We have, yeah, actually almost everyone. Okay, so I go very quickly. So what the principal component analysis does, that if you have n data points in k dimensions, so here k is equal to 2, you find the vectors that follows the data the most in terms of minimal square distance. So here this would be these 2 orange arrows. If I if I do this transformation on this random blobs that I just created here, I am not learning like anything super interesting. But if I just do this thing on the just up and down samples from the Icing model, I get this. And this is, I just recreated this from the Lei Wang's paper from 2016. So, okay, now we are all like machine learning experts. So this is not like a super shocking, but it's pretty amazing that like we don't have to study like 2 years of undergraduate physics. We can just do numpy.pca. And so what you see is that you see these 2 clusters. One is this, and one is this. And then you see the high temperature region here. And if you match the color of the blobs that are at the transition, you can actually guess the critical temperature of this phase transition like really, really precisely. Actually, so maybe now, for the sake of argument, I'm maybe I'm gonna skip this math for the PCA since everyone already knows this stuff. But basically, really, what you do is that you, yeah, please.
Question. Can you go back one slide? Can you
Totes.
point out once again how did you get the what did you do the PCA of?
So you remember that I was showing these two configurations.
You sampled them a lot.
Yeah, I sample them just with the MCMC, and then I do column vector from each. I do the thing, and that's my X matrix for the PCA, and then I am really just plotting the first two components.
Okay, so the first two components are one for the spins. Okay, and so the one the.
So the yes, is this very well interpret? So the temperature, that's just the color coding. So I like this, like the two components, they are really just the two biggest singular vector of this matrix that you get when you're doing the PCA. So I don't have like a correspondence with the spins. And then what I do when I sample is that I save the temperature, and when I plot the cluster, I color them by the temperature label of my Monte Carlo sample.
Okay, I think I got it. Okay, thank you. Thank you very much.
Okay.
Is it one PCA for the entire ensemble over temperatures, or does each temperature have its own PCA?
No, the entire ensemble. I just put all of them, like each sample is like one column in the matrix, and then I do the one PCA on that whole matrix.
And presumably then that PCA depends on the prior for the temperature.
Sorry, say again?
Presumably then that PCA depends on the choice of prior for the temperature. So you're uniformly sampling in the temperature between.
Yeah. So this is a great question. And then I just learned that we have an anomaly detection discussion this afternoon. So this is perfect. So the sampling that was done, okay, now this was like a while ago, but like is this just like Monte Carlo samples where you have for each temperature you get this acceptance probability. So it's not uniform in this sense. So you also see that there is a very little samples at the critical temperature because I am less likely to sample that. So and that's just a natural consequence of this like sampling technique, right? So if you would approach this with the anomaly detection, you can also do the same. But then you are correct that I could fool it by upsampling the critical region, and then I just get a colorful blob, and without labeling the colors, I don't know stuff. So
okay, so this is not robust to changing of the prior over temperature, and by sampling the temperature in some pathological way, you would mask the critical behavior.
That's correct. You could definitely do that. Yeah.
So if I get it correctly, you are saying that the first component is giving the magnetization, right?
The first component is being the normalization. Yeah, I guess.
So it's like the order parameter is really like the first PCA component.
Mm-hmm. Yeah. That's it? Okay. Do we have more?
So maybe I'm a bit confused of how you assign colors to this, because I had understood that for each temperature, you go through your PCA analysis, you find the PCA vectors and you plot them depending on, so how the colors are assigned here.
So it's like, so the colors, they are sort of pre-assigned in my data set, because when I draw a Monte Carlo sample, I'm like, this is the temperature. Yeah.
Okay, so you tell me the PCA component of each point after you have run the PCA analysis on everything.
This is
the T is, so the value of the temperature depends on the sample, and so each point has its own temperature. If you simulate, if you put, no?
Yes, that's right. Yeah.
So you are telling me there the PCA component of each point, but the PCA, you say that you run the PCA analysis on the entire data sample.
Yes.
So then for each point, you are telling me the component of that point on the PCA component 1 and 2, and you are labeling the according to the temperature.
Yeah, so right. So I put this, I put this color here so you see that it works, right? Like if we didn't do it blindly, you will not have the color axis on this thing. You will just see 3 blobs, and then you can think for yourself.
But I will still see the 3 blobs, so I will still see the 3 structures.
That's right. That's right.
Okay, now I can.
Okay. Like we still have some discussion going on, so I will let you finish. Yeah, no, this is fine. I still need to maybe invent a better way to talk about. I really recommend that you just click on the notebook and then you go through it, because like this is super hand waving, but if you actually go through the thing, you do the matrix, you do the singular volume, you plot it, and then it makes more sense. This is very like, yeah, I know that it's, yeah.
Just a minor question to make sure I figured that I understand everything's going on here. As far as I can tell, the second PCA component plays no role in anything you're saying here, right? So this could have just been a 1D plot.
Totally, that's
Okay.
that's true. That's true. Yeah, this is just makes a prettier plot. That's true. Yeah.
If I remember well, actually, the point here is that the magnetization, the order parameter, is linear of your degrees of freedom. That's why the first PCA gets it.
Yes, that's exactly the point. And this is really the underlying reason why it's so rare that such a simple, like, yeah, is the simplest model with the simplest order parameter. So this works, and I'm gonna show you in a second that how it immediately can break. Yeah, so maybe through this, yeah, now I already just told you. So I construct matrix X from all my data, and then I want to find a vector that maximizes the projection. So I project the data, I take the mean, I normalize, then I subtract the first component, and I continue. There is like a matrix singular value standard algorithm that does this. That is in the notebook, so you can just run it and see. It's not super deep. So this was again just to say that, like, this is, as you say, like, this is deliberately simple example that is engineered, and I color the points so it's very clear what it does. But for us, this was kind of very exciting thing back in 2016, because we didn't think about like phases of matter discovery like this, especially when even for this very simple model, it's actually pretty annoying calculation that you have to do, and you exactly have to be lucky that your order parameter is something that you can guess, so you can calculate it easily. Yeah, so this is just an example of another Icing model. This is called Icing gauge theory, and the term that is extra here is this product. And basically, really what the Icing gauge theory does is that now you don't have the spins at the vertices, you have them in the middle of the lattice. And then the low temperature state is the one where where the products over each plaquette are even. And if you start adding temperature, you start flipping some spins, and maybe for some plaquettes, you are going to get a -1. And this is the sort of just like a finite temperature crossover thing that happens in this system. It doesn't have an order parameter. It's just like this sort of loop constraint breaks. And the way to understand it is this sort of Wilson loop picture, where I just take all the spins that are one color. So I'm gonna draw, so that everything that would be up, and I draw the loop through it. And then it's very simple to understand where the phase transition happened, because the loops that are unbroken are all low temperature, because if you have everything, all the plaquette has even product, I can draw this connection without interruption. But if some of the plaquettes have odd products, those are exactly the plaquettes where your loops will break. And again, to my understanding in condensed matter physics, people spend a lot of time figuring this out. And yeah, unsurprisingly, you can plot PCA components left and right, and you are not going to see much. Okay, here I'm not gonna like explain anything. This is just like a show off, so I can also talk about my own research a little bit, just to say that like we also like actually sometimes use clustering with really like a great benefits. This is just the example where we built quantum devices from graphene, the so-called quantum dots. And these lines here, they are energy levels as a function of the perpendicular magnetic field. And what we did with those data is just we did one of those more like a nonlinear clustering techniques. In this particular case, it was a t-SNE, the stochastic neighborhood embedding, and all of the points have grouped based on their like quantum number pairs. So this is just to say that like I am really pleasantly surprised that when we move from PCA to this more nonlinear methods, it actually works in a daily research and gives a nice plots and helps us. And I imagine in like HEP or Cosmo, it's probably similar. Okay, but so that was just like a side comment. Yeah, please. Yes. It's like, I in principle agree, but we didn't like, it's one of those problems that we tried bunch of clustering techniques and none of them really worked. And this t-SNE worked in a like only in a very specific parameter regime. And I don't have a, because like, it's a complicated because each of these lines is described by like a bunch of quantum numbers. And then I like, yeah, so I mean, they are close in a sense that they have all like angular momentum is the same. So that's the kind of closeness. No, so actually, so here we have a, so this is okay, now as a, yeah, I think I can explain better if we have like a more time to actually talk, but you can write a Hamiltonian for a bilayer graphing quantum dot, then you do some things with connecting the boundary conditions, blah, blah, blah. You reduce it to the determinant problem. And these density plots here are energy magnetic field, and the color is the version of the determinant. It's value of the determinant. And then one dot is this determinant map and the same continue. You need to flatten, rearrange, then cluster. Oh yeah, totally. Like, did they look the same? So for example, the tau, those are the Valley numbers. So if you have a -1, it has to go down because you have this Valley splitting in graphene. So in that sense, that one is easy to see. And then those the M's, the angular momenta, they will be on a sort of similar energy scale in the determinant. So in that sense, yes. Yes. Yeah, exactly. Yes. We are good. Okay. Okay, then we can move on to more like a machine learning thing. And here again, I'm gonna explain something that you understand super well already, and that's a supervised learning. What a shocker. If a PCA lets me recognize the two faces of the Icing model, I can prepare these samples, give the ones that are below the critical temperature one label, the ones that are above the critical temperature other label, and just train a feed-forward neural network that recognizes one from the other. Just to show you that this is not a hard task, let's do a human Icing classification. So which of these are high temperature? Yes, yeah, BNC, perfect. Exactly, right. So this is actually not hard, and using a neural network is kind of an overkill. I just put 32 neurons in the notebook, you do what you will. But again, in 2017, this was the first time anyone used a neural network to predict these things. So this is Karaskia-Melko paper. And what they did is that when they put the probability distribution in output layer as a function of the temperature, well, over the coupling, you see exactly what you would expect, right? For one phase, it's a probability 1, 1, 1, then it's dropping. But then if you do that for many system sizes, they will cross exactly at the point where the critical temperature is. So let's say it's still a little bit silly because you are labeling the phases with the things that you already know, but you could sample far away from the critical point, do this exercise, and presumably looking at this kind of plot would tell you something about the critical temperature.
Sorry, how can you trust it to extrapolate work from the known regime to the confusing area where you have this transition? No, how do you trust that if you train in the borders, the extrapolation would look good?
Yeah, I mean, that's really like that's this key interpretability question we all have. Like for me, numerically, I would say that like the fact that all of these for all the different sizes that are sampled independently all cross in the same point is like a really good sign, right? When you plot this like finite scaling plots and all of them are going to cross like a 1 centimeter apart, then averaging the crossing and saying that's my critical temperature, that's probably wrong. But like if it all looks good, like this good, then I would say but there is always some uncertainty, as you say, right? Someone could bias your sampling and you could totally shift it a bit to the left or to the right. Yeah.
This is trained with an ensemble of like simulated data below the critical temperature and an ensemble above at
Yes.
different temperatures.
Yes.
And you could also, I mean, I don't think it's particularly useful, but you could also make a regression to the temperature.
Oh, on this example, again, yeah, I am just giving you like a
Learn a regressor, right?
yeah, that's what the network will do most probably, right? Like
Training with two samples, one which contains multiple temperatures would not, right? So if you do a supervised training, one
Yes.
is a set of different temperature simulation,
yes,
which there is like one state or the other.
yes,
Then it will learn to distinguish the gross feature between above and below the phase transition.
yes.
I was asking, I think probably it's a stupid question whether you could predict the temperature to have a regressor rather than just a classifier. So
I understand. So, yeah, sorry. I will get to this actually, like in like a 10 slides. Yeah, exactly, right? Because this is that's like a more like an unsupervised approach to this. We will look into it in a sec, because this requires that I already know the phases that I want to classify, right? So why don't label with something that we actually can measure or know from the simulation or something like that? Yeah, I am gonna explain that in a sec. Yeah, but okay. But now more back to this icing gauge theory. So okay, I apologize if it's bit grainy. Another quiz for you. Now, which one is which? Right. So now, if you don't see those Wilson loops, it's actually tricky. But if you know what to look for, you find that indeed the B is the topological one. But yeah. So, but indeed, right? So this is actually hard. But then it's beautiful that the neural networks work for this as well. Now, I just have a staple here because of what the audience is. I'm not gonna explain to you convolutional neural networks, but this is those like super fun example where just a feed-forward neural network doesn't learn it ever, because it would have to learn all the different combinations of all the, like you would really need to sample all the combinations of this thing. But if you give it a convolutional filter that is scanning, oh God, this one makes a horrible sign. If you give it a convolutional filter that is scanning with the correct stride, it will soon learn that it just needs to learn at 2x2 windows and learns to distinguish the filter, learns to distinguish whether they are odd or even number of colors in each square. So that was just like a apologies. Women's clothes, it never has proper pockets, like, okay. Yeah, so exactly as the question was now here, is that this is a little bit, this is nice, but not super useful, right? Because I know the phases, I label something, then I prove that it learned the thing. So the question is, what can we do to sort of have more unsupervised approach that actually would help us discover a phase transition? So I wanna mention two methods. The first one is learning by confusion. I'm gonna go through it quick on a boring slide, and then I'm gonna show you a figure where it's like this. You just guess your transition temperature. You train your machine learning model, and then you find what's the accuracy of your training. You guess the next one, you train the next model, and you continue like that. And then you see what's the accuracy as a function of your guessed critical temperature. I only saw this confusion thing in a condensed matter physics, but I'm sure it has to be a thing in other fields as well, right? So again, how it works, I'm sampling these two things, and I am pretending I don't know what's the critical temperature is. So I'm going to guess 2. Then I'm gonna train just my feed-forward neural network under the assumption that the transition temperature is 2. Then I'm gonna guess some accuracy, let's say 90%. I just wrote a number here, I don't know why. And then I make a new guess and repeat all of these steps. And then eventually what you are going to get is accuracy as a function of temperature. And you get this traditional W shape. It's good at the ends. Why? This someone can tell me. So the question is, why is it so you have this accuracy super high in the middle where the correct transition temperature is, but you have also super high accuracy points at the ends. So why is that?
Are you readjusting the weights of the sample, so you're always doing a training of equal sizes, or not? So you're doing binary classification,
Yes.
but it depends on whether you think you have equal sample sizes.
No, you have your sample, you have your training set, you just relabel it.
But you also don't adjust the weights to make sure that
No.
well, okay, then you only have one.
Yeah, exactly.
No, example.
Yeah. Yeah, exactly. That's it, right? That in the two extreme examples on the edges, you have everything from one class and nothing from the other, and vice versa. And then you have stuff in between. And then voila, there is a peak at the temperature that this I get 2.3, that's to the first decimal approximation, exactly where the phase transition in the Icing model is going to be. It doesn't always work this nice, but then getting this W shape, it's sort of like an empirical thing. You are doing things correctly, so this can be really handy. Yes.
Sorry, can you explain again how this method works? Because you got like one slide back, basically.
Yep.
Okay.
So
More than one. Okay.
we have our training set.
Okay.
And we did not assign any labels yet because we don't know what the transition is. So I am just gonna take a wild step in a dark and guess 1. Then I'm label my training set. Everything below 2 is 1. Everything above 2 is the next one. And I train one neural network that does this classification based on that. If I guess wrong, my accuracy is not going to be super perfect because on a test set, there are going to be some samples that are going to confuse it because I sort of labeled it wrong.
Okay.
You get it, right?
Okay.
And then I do this 10 times and eventually there is going to be one point that has the best accuracy, which is the correct point.
So just as a comment, so in high energy physics, this is known as classification without labels.
It's classification without labels.
Yeah, or equivalent to classification with noisy labels, and you actually only need to train at one temperature, it doesn't matter what it is. And then, assuming that the phase transition is sharp enough, you can just use that one classifier and you get a perfect separation.
So you just really would have like a one cut.
It doesn't matter where you put it.
Oh,
And then there's well, then there's strategies you can use to then turn that into finding what the transition is.
nice.
But
I
that
see.
assumes that there's only two categories. Of course, in the transition
Yeah.
region, you're gonna have ambiguous things. But if you
Yeah.
just have two categories, then it doesn't matter where you cut, you always get the optimal classifier.
That's true. That's true. Yeah. Thank you. Yeah. And then the other thing is sort of related to this. This is something that we did, and it's also what you asked about. This can still be computationally like bit annoying because you actually need to train a lot of machine learning models. And if you have a big spectrum, you need to also sample enough on your x-axis so you don't have your peak in the middle of the spacing of the two models that you train. So then this other, we sometimes keep calling it like a single shot way of doing this, where we say, let's forget about predicting the phases because it's hard anyways, and let's just predict something that we know. So in this case, we are gonna be predicting 1 over temperature, but we applied it to like other, like more, like let's say, like complicated scenarios where you can predict magnetic field or some other parameter that corresponds to some experimental knob that you can measure. So all I am doing now is that I'm gonna take a snapshot, label it with the temperature, and make a feed-forward model that, given a snapshot, tells me the temperature, which I know, so it's really easy to assess if it works. Just a super quick recap on how like derivative works. So if then this network works perfectly, the relation between correct and predicted parameter is going to be linear, right? Because my true parameter is here, and then this function should tell me that the predicted parameter is the same because I am doing, that's what I am training the network to do. And then if I take the derivative of the predicted parameter, I should get something flat, right? Okay. We do this again on this Icing model. I did again just a small demonstrator example, small data set, so it's noisy, but just to show. I plot predicted temperature versus the true label temperature. I take a numerical derivative of that, and voila, where the network makes the biggest mistake, so to speak, it's exactly the point where there are configurations where the temperature are really close to each other, but they are dramatically different. So this sort of prediction of, I take configuration, you give me temperature, this is the one when I can confuse the network the most. So I really just need to train one network to predict the continuous range of a control parameter.
Sorry, one second. I would have expected that in the place where there is a transition, the determination is more precise because it's very different. Like the structure of the system changes radically when you are close to the transition.
Yeah, but we are not predicting that they are in the different phases. It's like this, you have a temperature 10, and then you have a temperature 10.1, and those two samples are different. And I give two different samples, but I want to predict temperatures that are very close to each other.
Yes, but
The derivative is larger there. This means that the dependence or the relation between the two temperature and the length one is more precise.
I thought you say that the transition temperature, the error is bigger.
Yes, yeah, I shouldn't, that was too colloquial. I take that back. I am,
Okay, no, so then
yeah, I'm saying what he said, like, yeah.
What about this very large fluctuation at 3.2? Does this mean anything? No, at 3.2, like on the right.
You mean this
Yes,
one?
that one.
So yeah, I mean, so here this is just a very small, it's just a very small data set, and it's totally possible that if I am going to randomly sample and I only sample a few amount of configurations, you always have a possibility that you are going to sample something weird. So this just means that in our data set there was like a samples that were like untypical, And if you would sample more or make a better training on the x-axis, this would probably go away.
If you look at all the, like the uncertainty that you have on these points is so large because that point. okay,
Totally. Yeah,
So-
yeah. Yeah, really, this is just like, I wanted for you to have a data set that you can load in like 2 seconds and not download one.
How many samples did you use?
Oh my God. Okay, I don't remember on the top of my head. I wanna say 500 maybe. Yeah, so it's not, yeah, in total, yeah. So it's not, maybe it's 1,000, but it's 1,000 at most, like, yeah.
So I'm trying to do this in my head. If I just make a diagonal line and just look section per curve diagonal line, is that as accurate as the derivative?
Yeah, actually, maybe this is the, yeah, this is so here maybe this is confusing because here we plot, and I didn't manage to replot before the talk, the predicted minus derivative, so it would be like this. So it's exactly, no, that doesn't help because, yeah, you say I would just plot. I guess it depends how pronounced this is, right? Because if you have too small slope, then the intersection is also not going to be the best indicator. But I see what you're saying.
Right, this is your point, right? That at the phase transition, you should have maximum predictive power, and therefore you should be. bang
It's
on.
it's the crossed one. Yeah.
It looks good. Right, in the middle, if we were to draw, that's hard to draw, but
Yeah. Yeah, no, it's true. It's true. Yeah, I guess. Yeah.
Okay. Which it should be.
Then, so also another thing that is obvious. So with a bigger training sample, this curve will look more and more like straight. Right?
That's true. Yeah, so then of course, yeah, there is this like a fine tuning that goes into a different direction than we usually like, because we don't want the model to be predicting too good, because when it does, the doing this doesn't show you anything, because in the language of you crossing the thing, this is going to be so straight that you cannot tell the crossing point. And also then the derivative will be super flat. Yeah. Yeah, so yeah, this is just an example how it looks on the Icing gauge theory. And this, okay, this is still like kind of noisy, but this Icing gauge theory is really, really funny, because there is not a phase transition, just this finite size crossover. It was actually really challenging for the unsupervised methods, because all of this like other methods where you are using latent space of an autoencoder or stuff like that, without telling it, look at the damn subset, it just cannot learn just because of the complexity of all the different samples. So if you don't give it, this is the convolutional filter you look at, this is the Gaussian filter you should put. It was really hard, but this is the one method that is in a sense so simple that it can fool it, because you sort of abandon the topological constraint. You are just looking at the predicting temperature from the sample. So this was like at the time a way around going this unsupervised learning for the phases that are sort of tricky. So yeah.
Has anyone ever tried with graph neural network the same task?
Ooh. So I actually don't know. Like now people are using graph neural networks for a lot of things. I am not super aware of a graph neural network paper on this.
Just
Yeah.
curiosity. Yeah, it's not like.
Yeah.
Like the structure and the lattice is important, but the structure on a graph network is completely irrelevant. But you can redraw any network graph by pulling nodes and replace, as long as you keep the connections the same. So like a lattice, the structure is important, but on a graph network it's not. So you have a, as in, yeah. It won't know what its neighbor is. Well,
Yeah, maybe it's like one of those things where like if you would actually implement the correct equivariance, then it would work, but then you are cheating because you already told it that this is the placket thing, and without it, it's just going to be the same. Yeah. Yeah. So we use this method for like a bunch of different things. This is a sort of, yeah, doesn't super matter for non-condensed matter physics people, but I wanted to show we managed to map this phase transition in a ground state of the toric code, which is again famously annoying phase diagram. And this method can pick it up very nicely. This is like an important model for quantum error correction. I will not go into the details. Yeah, so this was the sort of path through like a sort of main branches that were like the foundational models that have been developed over the 5-6 years now to sort of found this thing illustrated on a very, very simple model. There is more that I am not gonna now, I would have to be here another hour, and also if it's a paper of other people, I am not the biggest expert on it, but there is, just to highlight a few things, there is a new paper on analytical predictors where they did what I just explained with the confusion learning and predictive model, but without a neural network. You can do like a 10 pages of math and you can calculate a statistical function that you can just calculate on your training set that is going to output what would be the thing that the neural network would have predicted. This also has some drawbacks because you by default discretize your problem and you don't have a neural network that interpolates. But I find this kind of method super inspiring because we just keep training, and lots of times it's not really needed. So they calculated this like optimal analytical predictors for supervised confusion and predictive model learning. And yeah, we've been now trying it on some new challenging phase transition problems and it works quite nicely. So this is just to say there are methods where you don't actually have to do the training part. You just need to calculate a statistical function on your training set. Yeah, then another thing that yeah, maybe we can also discuss more this afternoon. We also do the anomaly detection, sort of, yeah, as we said, for me, like the most naive thing to think about it, if I sample Icing model with the normal acceptance probabilities, the biggest, like the anomaly in the training set is the anomaly in the sample set is going to happen exactly where the phase transition is. In our field, anomaly detection is one of the handful of things that like actually discovered a new phase from a simulated data. So for us, we've been struggling a bit that we keep developing methods, and then we map what the neural network does to some condensed matter prediction done by traditional methods. And discovering of new things just from data was a challenge. But for example, there is this PRL from 2020 from Corbini and Kotman that they find a strong indication there is a new phase in one of the standard condensed matter models that we didn't know about. And then you can do things that I think you are also probably familiar with. You can do autoencoders, you can do GANs, you can look at the latent spaces structure, you can input conditional parameters into your GAN and tune the prediction. All of these things, I think we have all of us in common. And then I have here just in the corner, just to mention, I don't work on this at all, but there is also a quantum machine learning for a phase transitions. Basically, very naively speaking, you would, in any method that I explained today, you would replace the neural network with the quantum circuit that is parameterized like a neural network. The fun thing about this specific proposal back from 2019 is that lab at ETH Zurich actually implemented it experimentally. So we have a quantum computer phase classifier that is learning from data. So I guess if you are from a different field, this is not super like significant, but for us, this is very exciting because in a quantum computing, there is a lot of dichotomy between taking data, translating it into a quantum computer, doing the thing and getting it back out. Because if you actually calculate the complexity of doing this, you lose a lot of your speed up because it's complicated, right? Just because the operations on a wave functions give you a computational speed up, if you then need to read it out exponential number of times, then sucks. So doing the things that you can do directly on a quantum chips where all the information, you get a quantum data, you do the thing and you do a single measurement that tells you this is the thing. This is very exciting for us. So I just wanted to, if you want to later when I give you my slides, if you want to look it up, just that there is a sort of quantum classifier. It's very rudimentary. It has a very clear boundary of what it can and cannot do, but it's a first step towards what I think is a very exciting thing. No, I don't know why they are frozen. And yeah, so now let me formulate some open questions. I am going to give some details, but I hope that in a discussion we can generalize them and hopefully find some transitional qualities. So there is one kind of phase that is very hard for us to predict. This is something that I am working on right now, so I'm very excited about this. And this is very different than this, like you have a Hamiltonian, you do the temperature or you drive the magnetic field and then something happens to the ground state. You can sort of like very, very naively believe me that if I have a, I'm not in the window anymore. This one, yeah. Okay, so everyone knows what's a quantum circuit. Yeah, so we like in quantum computing, we just like write the calculations like this, that each of these things here is a qubit, a wave function of a qubit. And if I want to do an operation on it, I'm just gonna do a box and write a U. And if I want to do an operation on 2, I do a box and write U2 and so on. And then, so if I start from a state that is just like a product state of many separate, I can just describe that state by actually a small number of variables because each qubit has its own state. If I start doing quantum operations, I am creating the states that I told you about at the beginning that sort of span the whole Hilbert space, and then I have this 2 to the n problem. But when I measure a specific qubit, I can project on that state, and then I lower the complexity of the whole thing that was spanning my Hilbert space. So if I would think about strictly number of coefficients that I need to describe the state, or we call it's related to this inherently quantum correlation that we call entanglement, you can sort of just intuitively believe me that there is some competition between doing operations that keep correlating or entangling the qubits of each other and doing a projective measurements locally. And then you can think about this also in terms of a phase transition. And this is what is here. This is the probability of doing a unitary operation. So that's the operation that couple two qubits or create some complex correlated states, and probability of measuring. And so you actually get a phase diagram that as a function of what's your probability in each layer of the circuit that you do a measurement, whether you will have a volume law entanglement that's like everything is correlated with everything, you need an exponential number to describe it. Symmetry protected state, this is lower in entanglement but still correlated, but you can describe it with a polynomial of number of coefficients using, for example, neural networks or tensor network state. And then there is a trivial, which is like whatever. That's what happens when I just measured everything and there is no weird quantum correlations in the system. So the reason I'm mentioning is this, that, and this is something that actually took me a while to understand. All these models that I presented today, the Icing, and then you saw glimpses of some other ones. What we do is that we have a fixed model that has a fixed ground state that maybe is changing as a function of a parameter or two. But I have that ground state and I can sample from it as much as I like and do all of these things. Now, every time, if I draw unitary randomly, or if finite probability that I measure, every time I go through this circuit, I get a completely different wave function in the end. And the number of that scales exponentially with the number of different operations that I have here. So, and it's not super easy to create the same state multiple times because I would have to keep track of absolutely everything, post-select on each measurement, post-select on each random rotation that I do in my circuit. So that's quickly like stops scaling. Sometimes for small experiments, people are doing this, but this is not going to work in a large scale. So there is a super large number of the different states that I can create by doing this. So taking a sigma z measurement, which is what we did with the Icing configuration, spin up, spin down, just doing it on the qubits in a circuit here, that's never going to work because I always get a different state. So if I do one sample from it, useless, right? But even if this is true, this phase diagram has still been calculated. And even if you have this insane randomness in your circuit, there is still some fundamental properties about what is the probability that I measure, what kind of correlations I have in my circuit. And this is very universal and very beautiful. But all of these charge stability, all of these diagrams have been calculated by only for a subset of states that you can classically simulate, because you cannot do it fully generally for more than 10 qubits for this very reason that I just explained to you. So I am very interested in thinking about, can there be an unsupervised technique that I take some data, doesn't have to be the final measurement, but it cannot be keeping track of everything because then I am back in the exponential scaling, and adapt one of these algorithms to just predict, because this is the really step we need. Because if I can calculate this phase diagram only by keeping track of all the wave functions that I have, then I cannot simulate it. I can only simulate it for some states, right? So if I would have an algorithm that only takes measured data, I can just go to IBM quantum computer, do the thing with generating the random unitaries, generate a huge data set and find this. But so we have some idea, we've been working on this for a while, but it's actually surprisingly tricky. So this is just like a one thing. Yeah, please. We have a question.
I'm trying to figure out because the Icing model, of course, you can calculate the critical temperature, but if you're near a critical region, the criticality, you calculate the components of criticality, they are off. So the model is a mean field model. In your criticality, you cannot correlate only to the neighbors, it's a long correlation length. So, I mean, is it possible to use like a mean field model, like the Icing model, as you spoke, to this kind of entanglement states in which I suppose that you need to correlate everything? I mean, the mean field model, I don't know if does it work?
Yeah, so it's like not that I know of, because the moment you start doing approximations, the volume law sort of goes away. But maybe there is like, right, because is this tricky thing that this like really like heavily entangled state, they actually need all of the thing. But maybe one could think in this kind of terms, just looking at this like having some kind of low entanglement symmetry protected versus the trivial.
Because in the Icing model, of course, some spin will fill the interaction of the others, but indirectly, through the neighborhood. And so I was, because it seems like a different system, but I'm not sure. I'm just guessing it.
Yeah, like the sort of like challenging thing is that like here, because to get this statistical behavior, I have to draw the unitaries and measurements somewhat randomly. So it's, for example, not simple to write a parent Hamiltonian for the thing, right? But maybe there is actually some sort of more like a classical statistical model that does what you say. I just wouldn't know. I just wouldn't know how to write it at the moment. But yeah.
Neither.
Yeah, no, but this is interesting. We have another comment behind you.
So I think the main challenge is because of the topological behavior of these systems, right? Because the topology will give you entanglement. And one thing that one can try to think about is using the topological behavior, like for instance, topological deformation, which gives you the possibility to rotate the state without changing the entanglement.
Say again the last sentence,
So in
please.
principle, think about like SPT state. So we know that the SPT is topological and it's protected,
Mhm.
meaning that we can apply some type of rotation, which keep the state invariant, right?
Mm-hmm.
If we consider this one, then in principle, by having a very limited number of states, we can get the deformation out of these topological states and then do what we want.
Yeah, yeah, that's true. That's true. And this is exactly how people like calculated this kind of things, because if you actually have a wave function, you can calculate your topological cross entropy or ancillary cross entropy, and all of these different entropies, they can pick up the different things. And now really the challenge is, what can I easily measure that would let me approximate those things and feed them to the model? But exactly, right, you are identifying the correct thing in that sense that no like simple measurement is going to do. We need to find the sort of entropy or entropy-like quantity that is complex enough to capture the topological aspects, but I can access it experimentally without, running this 100 million times and post-select on 1,000 circuits that I wanted. So yeah, that's exactly the correct thing. Yeah. Yeah, maybe I'm gonna move to the next thing. Another thing is a question of interpretability, and here I think we might have a more overlap between different fields, because now when I'm presenting some of these methods that we are developing for some sort of complicated topological phase transition, the first question that I get at any conference is like, but what if I give you one that I don't know? How do you know what kind of phase transition it is, which method to use, blah, 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 right? And so now what I say these days is that I don't, but I can do this hierarchy that I walk you through today. I do PCA, doesn't work. I do nonlinear clustering, doesn't work. I do learning by confusion, doesn't work. And then I do the predictive model and suddenly it works. And just like from knowing for what kind of methods are excluded that the previous one doesn't work, I get a sort of a guess what kind of crossover / phase transition is happening, right? But that's not very satisfactory. That's not very satisfactory thing. So, and like in quantum physics, this is actually really tricky because the data we take are limited. So yeah, understanding what are these models, what are they learning, and what we can actually say about the phase transition, that's a really big question for us at the moment. I wanted to highlight this paper from Warsaw and ICFO by Anna David and others, where they are doing this kind of interpretability experiments by calculating different measures by sort of ranking the points by the importance. You could, for example, imagine that you train a network and you remove one point and you see what happens to the loss function and what kind of new minimum you find. And then they have this whole framework where they quantify importance of each training points. And then based on which are important and which are not, maybe you can say something and stuff like that. So there are this sort of, these methods, again, they existed outside of physics, but like beyond that, we don't have super much. In some of our papers, after the network learned, we were able to make like an educated guess and calculate some quantity. And see that that quantity predicts the same thing what the network has learned. So if you have a good physical intuition, you can make a guess, but it doesn't answer this question that like, I get a data, I don't know what it is. I'm going to apply this unsupervised predictive model on it. I get a peak at 10, and then I am like, so now what? Is there a phase transition? Is it just a blip in the data? What kind of phase transition it is? This kind of interpretability questions, I feel this is exactly what like everyone is super interested in right now. And we have special cases where we can explain very beautifully, but I feel we are missing general methods. So I would be super interested to hear if people have opinions on this.
Yeah, so on a similar note, in language modeling, say you have you want to caption an they have these attention networks, which is a specific architecture, and you can basically learn what part of the image the model was looking at when it generated the caption. So if it's a picture of, like, it's really quite impressive. Like if there's a bird flying through the sky and it captions this as a bird, when you like hover over the word bird, you can go back through the network and see how strongly it was looking at each pixel, and you find that often it's very condensed around the bird and it's not looking at the background. So in that sense, you can sort of see configurations, which configurations are important to your network. It's trying to tell you there's a phase transition, and if those all lie near each other in some temperature range, maybe you could see that as some interpretability. Like it's not looking at loads of configurations from random places; it is looking in some range in some sense.
This is nice. Yeah, because of and then you say how to say, so am I getting more like this than just, let's say, plotting my convolutional filters? Like, that's not like a evil question. I'm just
No, yeah. I guess it's more of a generalization to a case if you don't have a convolutional filter. You sort of like learn a way. Yeah, in a sense, yeah, you're learning how strong you're looking at each point. So it's sort of like a value.
Yeah.
It's like it was a generalization of the the gradient of the output with respect to the input. Yeah.
Now the filter will have to go also to everywhere the image. Sorry, yeah. The attention will focus in a specific region. No, the filter will be the best filter that when you move it across the image. So in some sense, this is a bit more. It really points to a specific place in the measurement in the data sample and for each data in the feature space that you're interested in some sense. No, that's what you were proposing.
Nice. Yeah, this is cool. I think it could be fun to just try one of this. Yeah, just try the attention network and see if it can pick up one of this, like where the placket value matters or something like that. Yeah, this is nice.
Yeah, I'm sorry. Also, what happens if you have multiple phase transitions? Now, if you have because in that diagram I see three phases, so you have different types of phase transitions you can have. Can you detect in your model if you train for 2, but there was one hidden that you didn't know about? With this type of methods or not?
Yeah, I guess it was your question. You also asked me about this outlying peak, right? Yeah. So a lot of this is not going to work because, for example, the learning by confusion is predicated by me labeling, but more of this like this like predictive models where I'm training on a generic parameter. If you train over several data sets and the second peak doesn't disappear, then you have a second phase transition. So and I saw the same for this analytical predictors that replace the neural network. So I think this most like agnostic things work, but whenever you are labeling, then you are right that it will fail immediately. Yeah.
Thanks.
Yeah. Thank you. Yeah, and then really my final point is like super general. Maybe I am gonna bring this back up after lunch when we meet here for the anomaly detection. It's again, like as I was saying, we have a few like small examples where there is like a very specific Bose-Hubbard model and people knew about 4 phases, but maybe we found a 5th one with this method. So I would be just interested to hear where like other people are standing and this like, you know, completely unsupervised discovering. Like, does it happen in like a high energy physics that you run some anomaly detection or whatever unsupervised model you are running and you actually like discover a new physics? Or are you still operating in the regime that like we knew it's kind of there, but now we have more efficient way to check that is there and find more reliable proof because we can do it readily from the measurement data? So this is more like a more philosophical question for my stay here, but now our field is still, especially in like condensed matter and quantum information, this only started like 6 years ago, so it's still kind of young, but we are still not shifting from the developing better, more efficient numerical techniques that are more suitable for experiments than other things to this is very robust way to that you should run your experimental data through before you do anything else, because that's the way you discover a new physics. So this is like a final question. So I don't know if anyone has now any thoughts or comments on this, or we can just revisit this in a later discussions.
Me and Gaia were sitting around the day concerning what you were saying, was, yeah, I don't know, philosophical thing. I don't know if everyone here agrees, but probably in any physics we will have something that we call the discovery. On the day we have deep model understanding of what we are seeing. Okay, so but this is for us that like the target, the goal is the model. Okay, so I think a basic philosophical attitude is that we may use these techniques to enable finding out things that we don't understand in the data. But I guess the Nobel Prize will be given the moment someone makes the like first principle theory explanation of this data, which will be enabled by anomaly detection. But anomaly detection will not be the discovery. I don't know if anyone disagrees.
Yeah.
So I'm curious. Have you learned more about what the definition of a phase transition is, or what a phase of matter is, through this work? I mean, if you the way that I usually think about phases of matter is something where I have a system that I can study theoretically, and I can understand theoretically what phase I'm in. But if I'm really asking, is a phase of matter seen or be able to see with just the data itself? Like, is that a direction that your own brain is going, that say that the definition of a phase of matter should only be determined by things that are observable and not about things that I don't actually have in principle experimental access to? Does the question make sense? Like, do you have a new insight into what a phase of matter even is defined as through this machine learning approach?
Yeah, I would say yes, right? Like not on like some super like fundamental level that we like discover new physics, but a lot of these things, like for example, in all of these topological models, like you need to know which like loop or whatever to check. But then we discovered that it's not true. Like I can do this like predictive model on a data from the toric code and I find all the phase transitions just fine, because eventually it will just learn the differences between the phases. So in this sense, I feel like all these different phases are kind of more similar than I thought they would be. Or for example, you have like some topological, okay, this is like super in progress, so I wouldn't like put my, like I wouldn't bet my life on it, but like there is a lot of these phases where you have this like indicative mode that appears on the edge or in the corner or something. And that's the thing that we can experimentally look at. But like, again, if I cut out those visual modes, what drives the phase transition is still happening in the bulk. And I can trade this kind of model on the bulk only, and it discovers the thing. And then there is all this entanglement phase transition, which is like super weird, but the underlying principle is the same. And then this Icing gauge theory, it's not even a phase transition, it's just a crossover. And like, just seeing that like there is some very like a general class of methods that does the same thing for the transition, for the phases of matters that we thought about as a diametrically different, is very interesting to me. I don't have like a one like underlying really like this is the new, like this predictor is the new formula for any phase transition, but just seeing that it works like this and everything is accessible just by doing basically a projective measurements or expectation value measurement, that I think is very, very exciting. Okay, then thank you so much for being such an active audience and for listening. And I'm just, I am here for the next 2 weeks. And on Monday, I am gonna give more of a, what are our latest results kind of talk. But I'm looking forward to talk to you about physics. Thanks.